Hello, Tensor friends. I got a question about one of my videos. I made a statement without any backup. I said the covariant derivative in Cartesian the coordinates is equal to the directional derivative. It's just the same thing. And the question was, why is that? And it's much easier to show that and then a little bit of math than it is to explain it in the comment the section. So that's what I'm going to do. Okay, here's our Cartesian coordinate, the system. We got our two, the favorite, the basis vectors, right? E1 and E2. You might call them I, J. You might call it X hat, Y hat. They're all the same thing. They're 1 unit long and they're 90 degrees apart. Okay. Now, what makes this such a nice the coordinate system to work in is because if I take this point and start dragging it around, look what happens to the basis the vectors. They don't change. They're the same everywhere. Okay. So what happens now if I superimpose on this a curvilinear the system, like plane polar the coordinates? So let's drop a line the segment back to the origin. We're going to call that R because it is the radius of a circle. And we're going to define an angle between the x-axis and this radius here. And now, since we have two things, a radius and an angle, we can define our the basis vectors in the coordinates. So here is ER and here's E theta. Okay. Now, watch what happens to ER and E theta when I start moving this point around. Look, they both change direction and the E theta changes magnitude. So ER is a unit magnitude, so it doesn't change its length, but it changes direction. E theta changes both length and direction. All right. So these are curvilinear, the coordinates. And this is the major difference between what the question was based on. All right, so let's go look at a little bit of math. So we've got a vector, which is expressed as a linear combination of its components and basis vectors. And we've got contravariant components and covariant basis of vectors. We want to take the derivative of that vector with respect to a coordinate. Okay, so we use the product rule. We get the first times derivative of the second plus the second times derivative of the first. Now, this is what you usually see in vector calculus, where you're dealing in Cartesian the coordinates primarily, and this is the directional derivative. But here you've got this extra term here, right? This thing. Now this is derivative of a vector. So derivative of a vector is a vector. So we can express that also as a linear combination of its components and basis the vectors. All right, so let's put that back in there and we get this expression. Now look at these indexes. We've got two summation indexes, I and K. So we can swap these around. They're called dummy indexes in tensor calculus. So we can swap them around. It doesn't change anything. So I'm going to swap I for K, upper and lower, and we get this expression. Now I can factor out at E's I, and in doing so, it leaves me with this in the parentheses, okay? And this is what's called the covariant derivative. So it's saying I'm taking the ith derivative, the jth derivative of the ith component is equal to the normal directional derivative you would see plus this stuff. And this is the connection, it's called the connection coefficient, the Christoffel, the symbol. So it's connecting the fact that the basis vectors may be changing in the space when you do the derivation. All right, so let's look at this in Cartesian, the coordinates, just 2D. All right, so here's our generalized equation. And we're going to choose the derivation of y. We're going to take the derivative of the Vx component with respect to y. So our free indexes are I and j. So we go through and we fill in all the i's and j's that we find. Then the k is the summation index. So in the first case, it'd be x. The second case, it would be y. So now to find this out, we need to find these Christoffel, the symbols. Well, what are the Christoffel, the symbols? Here's the way they're derived. You need the partial derivative of the metric tensor with respect to these coordinates to derive the Christoffel, the symbols. Well, what's the metric tensor in Cartesian, the coordinates? It's the identity matrix, because these are orthonormal bases of vectors, right? So E1 dot E1 is 1, E1 2 is 0, 2 1 is 0, and 2 2 is 1. So the derivative of this is 0. So the Christoffel symbol is 0. So if that's 0 and that's 0, then what we're left with is the covariant derivative is the same as the directional derivative. Now, in plane polar, the coordinates, these are not 0. This is actually 1 here, and this is r squared. So it's a variable. So that's the difference, and why it's true and why it isn't true. Okay, I hope that helped, and let me know if it didn't. I'll see you later.